Without having edge computing in orbit, it would be a difficult task for our satellites and our stations, which have these amazing sensors that collect terabytes and petabytes of data, to process the data on location. What they do instead is they pass that data down to data centers on Earth, where whatever compute they're trying to do happens, and then that information gets set back up. And if you start to add all the time together, you realize you can't do things in real time. You can't do missile tracking. You can't do real-time air traffic control. You can't do maritime tracking. You can't do environmental catastrophe tracking. None of that can happen local to the satellite and provide that the computed information back down to the resources on Earth that need that information. So by moving the compute out to orbit, you remove that bottleneck immediately.
So what separates Sophia from all other companies today that are entering the business of computing, large-scale computing in space, orbiting data centers, and so on, is the fact that when we conceived Sophia Space, we began with basic first-order principles that today differentiate Sophia from others. Those principles were, when we look at the computing infrastructure on Earth, we made a decision to design the Sophia building block elements, not based on decisions that were made for them to work on Earth, but to remove everything that was part of the design for Earth and only use those elements that we need to add for space. So when you look at the mechanical thermal structure around computers on Earth, including in data centers, they are all designed for thermal management using convection cooling. In space, the thermal environment, the environment in general, the vacuum, and the environment of a spacecraft is very different.
The thing to keep in mind here is that space just punishes terrestrial assumptions, it just does. And physics is always going to be with us. So we're taking the approach of the problem to solve first is the thermal problem, the thermal shedding problem, and we think we've done that. So designing systems that don't need large heat pumps, that do not need shielding to protect those heat pumps, that do not need infrastructure around those heat pumps is key here. And so having a system that natively sheds heat through radiative methods only, that allows itself to scale, that allows itself to build just out from a single server out to many servers and have that heat scaling problem solved from the get-go is job number one.
2, 1, mark.
What is different here is we have a deep bench of expertise coming from NASA and JPL. These are people that have done this before time and time again. And by done this, I mean the aerospace process of packaging up satellites and observation centers and Mars landers and lunar orbiters. They've been doing this for decades, so this is not new territory for them. The other thing that stands us apart from the crowd is rather than fight the space environment for computing, we've rethought what it meant to be in orbit with a computer. So a lot of our competitors are looking at terrestrial computing solutions and retrofitting them for orbit, which means active cooling, which means repackaging existing servers. What we have done is we've rethought the way that computer should operate. We've looked at orbit and said, okay, this thing is going to be moving very fast. There's a lot of solar power. It's 4 degrees Kelvin. There's a certain amount of radiation at the level we're going to be at. Rather than fight those things, how do we make use of it all? And that's when we came up with the tile. So the tile is a flat object, not just because it looks cool, but because the components that power the computer are flat against the alloy that we're using to dissipate heat. So when you have a heat source and you're trying to radiate that heat out, you're going to get the biggest bang for the buck when you've got the largest delta between the heat being generated and the space that you're trying to radiate the heat into. So in orbit, when you've got CPUs and GPUs generating 120 degrees Celsius heat, radiation happens fairly quickly. So the biggest differentiator that Sophia has from our competition is the way the tiles are designed, the way we thought about computing, the way we thought about modularity of all of our computers, and the way that the operating system is going to handle the distribution of load and compute on those devices.
We believe very powerful systems are going to get built in single-digit years.
It's no longer this thing that was going to come. It's here now.
It's an infrastructure of intelligence.
Vastly more data.
There's not enough energy on Earth to support the computing power needs for AI.
People are planning 10 gigawatt data centers. Gives you a sense of how big this crisis is.
Data centers in space could help alleviate that problem. It reminds me of the internet 20, 30 years ago, when a lot of things happened for the internet to take off. Put a lot of computing and a lot of data storage in one module. You launch, it opens up, and it's a data center with all the computing and all the storage, all the communications embedded in the structures. A constellation of satellites connected with optical communication. Each module is a large deployable structure, and each structure has a number of tiles. Each tile is analogous to a server rack. And that tile kind of is almost like a small spacecraft in itself. It has solar rays on one side pointing to the sun. It has servers embedded on the back end. And these tiles are independent. You can put hundreds or thousands of them in a single module. And that's what makes up the data center.